Okay. No. Is it asking me for this? It's never asked for this token thing. Something else. Let me shut this thing down.
We weren't supposed to run on Colab?
No. Oh, we can run on Colab. I just thought, okay, I have to go and then do a bunch of things. I just thought I'll run it here.
Okay. Yeah, I did it there too.
Okay, I mean, it wasn't big to, I mean, you could run it on this. So I thought, okay, why not run it on this? And then we'll come back. I mean, if you want to run it on Colab, we'll run it on Colab.
No, I'm fine. I did it on Anaconda.
But the thing is, you will have to, let me see if I'm getting the same error. I'm going down here. This is kind of, oh, hey, we thought we were running out of people. So I had already saved the engineered table here. Remember, he goes through a bunch of engineering, feature engineering.
Yeah.
Because I thought, okay, let's focus on the deep learning stuff rather than focus on all the other stuff. So then I did all the feature engineering, and then I saved it as a new pandas frame. If you look at this here, let me open up this. Not the dlib thing. I'll show you what it means. Okay. Let's see if this dlib thing is going to throw out an error. That means then I have made some change and then I didn't. Okay, that's not 2. If that was 2, then I haven't done this. That should have been. Yeah, I didn't get an error. This is this where you got an error? On from dlib model, that's what you got an error? Because you may have gotten an error. I just want to make sure if the feather means then you don't have that files that I have.
Yes, so you didn't have to install like Dateline and all this other stuff, Datetime, TQDM, or you already have those, right?
I already have those.
Okay. Yeah. ISO week. Okay.
I already have those. So if you hadn't
Yeah.
installed that,
Yeah.
then it's going to give you an error.
Yeah. So I installed those, and then yeah, the delete part I got that.
That's my stuff, but this would be different in your case. I mean, we can open up a Colab. Let me open up a Colab then, if you want
Okay,
to
did yours?
do it that way.
Yours.
Okay, he said something, I'm in. Okay, good. He's in, and then the Google Drive. Let me go to the Google Drive and see if I have it there. May not have it. Yeah, I may not have done a thing on the Google Colab. I mean, we'll have to do that. What I do is you need, I don't know if I saved this file. I mean, I need to send you guys this file because otherwise you won't be able to run with it. Okay. Which is like, got to save it somewhere. Because I did all the, I mean, I went through his bunch of, his 3/4 of that notebook is about feature engineering. Yeah. He does. So I went through all that, and then I said, I then saved this Rossmann joined. Okay, and the joint test. See, right? Yeah, you need that. Yeah. These are the two that have been feature engineered. Okay. So if you look at this, what I did, the way I created is, I mean, you can run through this. If I go to lesson 3, I went through his whole thing. This is his lesson 3. And so, and then you have to get this data set from here, from the Kaggle competition, which if you go here, oh, okay, well, it downloaded the TGC, but it's there. I didn't want to download it, but if you go to his link, you'll be able to download that. Then you go through all his stuff. See, he concatenates the stuff, how he reads the file. Okay, and then he's bringing in Google Trend and weather into it. So if you look at that data set, so this data set is a bigger data set. See, there is a weather.csv and Google Trend.csv and stuff like that. So there is a bunch of other files he brings in, and then he's concatenating it. And he says the feature spaces, nah, these are the table names, the train, the store states, the state names. These are all given by the Kaggle competition, these 4 things, and the test. What is not given is the Google Trend and the weather. So he goes and reads all that stuff. As I said, you can go through that. It's a bunch of feature engineering because he's saying what is the day of the week. He's doing all that things there. I mean, in the tables, in the, where's that? Table.head. Okay, they are giving the week number 1 and the store number 1 day of week and all that stuff probably. And then he's going through all these different tables, and he goes through a bunch of tables. I mean, this is where he gets the weather data here in that area. The 0, 1, 2, 3, 4, I mean, which refers to and then he's getting some Google Trend data in there, what people are searching for and stuff. So you have to go through that. I mean, it's a big thing. I mean, he just goes through it, and then there is NAN values and all that. He's summarizing everything. And so he does a big feature engineering. See, data cleaning, feature engineering. Yeah. So he goes through all that stuff. So what I did was I went through all that stuff. because he's saying competition open month. When was the competition open? What is the promo? The holiday, how many days before the holidays, how many days after the holidays, all that stuff he does. And then ultimately, he comes here, somewhere around I said, well, I said 75, but it's not because I did a few things, create features. See, this is where I said to feather these two files, the join and the join test, which is all featured engineered. And then here is where it starts. Here is where the deep learning starts from here. So I said, okay, let's not, I mean, that's something that's about machine learning and all that other stuff. So I started here with this join and join test, which is all the feature engineer. If you see here, the join head, I mean, this is the store, the day of the week, date, sales, customers, open, promo, state holiday, school holiday, whether that date is a state holiday or not, whether it's a all sorts of stuff he does. Year, month, week, day. You have to break it up into the date, into all that thing, so that the model can recognize what it is. And the day of the year. It's not only about, hey, the year, the month, the week, and the day. You also say what is the day of the year. In 366 or 365 days, what is the day of the year? And is month end, is month start? I mean, a month end, he has 731 as a month end. Is it a month start? So because the deep learning is not going to know what a 731 is versus a 630. I mean, it has to know, okay, that's a month end, and the 630 is a month end, and a 731 is a month end, so that it can find any correlation based on that. And then, is it a month start? Is it a quarter end, quarter start? Is it a year end, year start? How many seconds have elapsed? And stuff like that. The store type, assortment, competition distance, how far is the next store from here, and the open since month, promo, how many promos or something. You have to read through the Kaggle competition, this promo thing. And then he adds all the weather data. Hey, how much visibility is there? What is the mean visibility? Sea level pressure, the wind speed, the cloud cover. He just keeps adding so much stuff into this.
So for the missing data, is he just encoding it as NAN?
Yeah, he's just encoding it as NAN. So it'll be a category.
Yeah, so there's several ways of doing that, right?
Yeah.
You can do NON, you can do one-hot encoding, you can do...
Yeah. No, you stay away from one-hot encoding in this, in deep learning,
No,
okay? It's like you, yeah. Because you can do embedding very easily rather than do one-hot encoding. It's just much easier.
Into the embeddings? Into the embeddings?
Yeah, he does the embeddings later. I mean, as you see here, so this is all the speed. I mean, NAN, he may even remove this. Who knows whether he's going to, because he's going to take, after all, these are all the like fog, if it is a fog, wind degrees. And I mean, there is tons and tons of feature engineered and more data on top of this. Hey, how many days it is after a state holiday, and how many days it is so that the model can find anything that it can find.
Because they deleted that in one of the...
Oh yeah, they said, yeah, deleted that, and they shouldn't have. So then he describes what are all the categorical variables. So he's saying these are the category variables. That means they are not numeric in the sense that
continuous variables
you leave it as it is. That's what he goes through. The categorical variables is what you have to send it through the embedding layer. Because if I have 1,000 categories, if I do a one-hot encoding, I have to have 1,000 zero with a 1, 1,000 column vector. I don't want that. I can do an embedding with 50 embeddings for 1,000 categories and be able to represent all that information. So, and then he's saying, what is the dependent? I think sales is the dependent variable. I mean, that's what you're trying to predict, dependent variable. And join, so he's saying, hey, don't give me the whole thing, just give me these categorical variables and these continuous variables plus the dependent variable plus the date. He's saying the date. I don't know what he's going to do with the date, and then he's just doing a copy of that and join test, and then here's where all the and then this is the test, and
Yeah, what is he doing?
using. Okay, so first, before you do the embeddings, a lot of the categorical variables you got to put them as numbers in some fashion. You can't, I mean, because a lot of the categorical variables, say there is numeric, alphanumeric stuff in there.
Yeah.
Say there is words and stuff, we'll see that in NLP, but you have to represent it in some numbers.
Enumerate it.
You enumerate it, yeah, enumerate it. Numericalize is what he uses. That's what the attached text thing is called, numerical.
If you programmed anything,
Yeah,
enum is a.
yeah, enum is a, yeah.
Also, the labels have to be
Represented as numbers. So.
And then after that, you do the entity embeddings of those labels.
Yeah, of those things.
Right.
But then you also keep what that A is E1, B is 2, and all that stuff. You have to keep track of what the thing is, because when you come back later with the test thing, you have to then convert all that category into their is the key. Yeah, the key value pair. You have to remember the key value pair.
So embedding.
And then he does the embed, because all it'll do, if there is 1,000 different categories in there, all it'll do is the enumerating will do 1, 2, 3, 4, 5 to 1,000.
Embedding only works with exclusive categories. I mean, they can't intersect.
What do you mean?
Meaning you can't have two different categories for the same.
How will you have two different? No, you can't have it two different ways. I mean, a category is a category. You can't. I mean, then you have to create another variable.
Yes.
Another thing, and then
these have to be mutually exclusive.
Mutually exclusive. Yeah.
That
I mean, 10
can,
means it has to belong to only one category. The number 10 has to belong to only one category.
Like it can be a cat and then a breed of a cat. That's another category in the same variable.
Yeah, in the same variable. Yeah. No. That's why you do the tokenization and stuff. That's why in the NLP, I mean, a breed is one token, cat is one token and stuff. But what will happen is, when you do this embedding, when you learn this stuff, the breed and the cat will be close to each other.
Yeah.
It'll learn because in the thing, because it sees that they are all occurring together and stuff. So it'll figure out that embedding is that, hey, breed and cat are close together.
They had a thing where they had done king, they subtracted the word male.
Yeah.
And gave queen.
Queen, yeah. 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 So.
Otherwise, you'll get a ruler or something like that.
Yeah.
Or a royalty or something. I don't know.
Oh, that, remember that deep learning we went to with what's his name, Biguta? That one was about this stuff.
Yeah.
So, I mean, you want to play around with it and see what it does. Okay, here is where you would say, hey, apply cats to this. Then see, okay, what is it? What has it done? So, I mean, we can do that. I mean, if I go here, I will, because that's when you know what is actually happening.
Where is it defined how big you're embedding?
Well, we'll see that. I mean, yeah, later. Yeah. So there is a heuristic that you use based on how many categories are there, how much embedding you have.
Oh, yeah, the cardinality and everything.
Because technically 1,000 will fit in 10 bits. Right? But 2 to the power of 10 would be 1024. You can fit the whole embedding into 10 bits.
But they have a,
I mean, if they're floating point, okay, 10 floating points.
yeah. I think he has a restriction on the size of it, right? That's something.
So could you just use 10 bits as your encoding?
So if he does that, I mean, let's see what joined became. Did it do anything? I don't know. I mean, just trying to see. We'll have to check on some categories. What is it that he was using? I mean, he said store, day of week, year, even that he's saying is a month as a category. That wouldn't have changed anything. And the state holiday is still coming fall. So I don't know. Apply cats would have done is it created, what did it create? Because it's not even a returning function. It will have created a DF. That's what it did. It created something called a DF, I suppose. No. I thought DF in N. What did it even do? In DF into categorical variables using train as a template for category codes, changes any column of strings in DF. Okay. DF, okay. It is about how do the test know what it is needs to do, I suppose. I mean, this categories is saying something about how very difficult to know what it is doing. Strings in DF into categorical variables using training as a template for the category codes. So if there is any string, was there any string in the joined is the question. Well, this would have it already took care of all the strings here. As type category, cat is ordered. State holiday. Yeah, we'll have to go. I don't know what it did. I have no idea what is done. This applied cats is done. Here is where he's doing something about total number of elements and they get a list of index values for validations. Okay, that's just trying to break the thing into validation sets and stuff. So yeah, so he's breaking that. I mean, what he initially does is he does that and says, I don't want to train the model on the whole data. I want to train it on a subset of the data on like 150,000 rows of data instead of it contained something like 844,000 data. So he's saying he gets some CV index. I mean, he says, I don't want to do it on the whole data, and then I'm going to do it on this. And these are standard, I mean, sklearn things where standard scalar and data frame mapper. And here's where he's doing the fixed missing data in a column, DF with median and add the data was missing. So he does more stuff, more of how do I replace his null and stuff, and he replaces it with the median of that value.
The missing data.
The missing data.
He's using the median.
Yeah, he's saying the median. The median.
Only doing entity embeddings on certain categories?
No. Embeddings will come later. Let's.
Okay. after getting the median.
Yeah.
Oh, sorry, this is for missing.
Missing, and then numericalize. Here is where finally he is numerically. He hasn't numericalized it before. Here's where it's finally doing this, which he calls numericalize. Changes the column from a categorical table to integer codes. And then he does a few more things. Takes the data, splits off the responsibility, changes the different entirely numeric data frame. Yeah, you have to go through. Before you get into the DL thing, there's a lot more stuff he does.
Yeah. But this is kind of important to know because I think a lot of the work
in time series is about like all these stuff that you have to do. Then he does some mapper, and then he takes the log of the he takes the log of the y instead of y, because y is a huge number, and he's taking the log of the y. And I don't see where he has normalized stuff. Usually you try to normalize.
Log of the sales.
Yeah, log of the sales, that he does, but I didn't see where he normalized the continuous variables. Oh yeah, he does scale. He does the standard scalar. That's where he's doing a scalar. He does normalize it. Not normalize, he's scaling it down to the same scale, all the continuous variables.
Oh, okay, got it. So that one isn't too bigger than
too big, and this one is too small, kind of thing. Then he does, okay, and then the mapper, and he has a bunch of cross-validation is not run instead of holdout data is generally the most recent data. Okay. Somehow I didn't define the mapper. That's very surprising that I thought I'd run it before, but probably not. How is the mapper not defined? Mapper is equal to mapper. Oh, I didn't do this. I didn't do this. That's why. Yeah, I did something before. I'll go back. This is fine. I think I was just doing it one more time. I'd already done the index. Let me get rid of kernel settings or view. Clear output so that I don't see this. Okay, that worked. Then he's doing validation from the train stuff. Here's where now you get into the deep learning now. He's defining a columnar data set. This is to define a data loader for the thing. And because it's getting, I did this at least 3-4 weeks back now. I'm trying to see again, because once you have to return, when you go the data loader, it returns what the categories, the continuous variables, and the y variable, and it'll return it in a batch, however batch size you want, what batch size you want. And he's saying what is my categorical variable. He's saying stacking it together, and on the continuous variables he's also stacking it together, all the continuous variables. Okay. So self and then the
else empty zeros.
Yeah, if if categorical variables, if there is no categorical variable, if there is nothing, then it just has a bunch of zeros. So he's putting it in a fashion, one list of one array of continuous variables, one array of categorical variables, and then the target variable. That's what this is going to return. That's what this is going to return. Where did I go? Yeah, the columnar data set. That's why he's stacking all the stuff into a row like this, and we'll see that it'll return this thing because he's going to use that in the deep learning model because he's going to put the categorical that array into an embedding layer, but the continuous variables he won't put it through an embedding layer. So he needs that, and then once it is passed through an embedding layer, then it'll concatenate all those stuff into a full thing, and then you'll have additional layers that will go through. Yeah, this is just, hey, how am I going to load the data? And we'll see that this is just to get that class going. I mean, you're going to say, hey, from data frames, columnar data set, data frames, and you're going to supply your categorical variables, continuous variables into this. And so if we go through that, then this is again split each array passed by this. He's just splitting. Okay. He's just creating a validation and training DF from this. That's all he's doing. He's just saying split by IDX using the validation IDX he created before and create a val DF and a train DF and this, and then he's going to just split it like that. So it's a simple split he's doing. Now is where you then define what the data set is. This is the data set. And then the data loader will come after that. This is just the data set. This is the data set. And then the data set has to have these methods. So data set, column, data set, train from this. So he's going to supply what is my training data frame, and then the categorical variables and their y, the training y, and then the validation df and the categorical variables, and then the val y. Anything that is not a categorical variable is a continuous variable. That's how they figure that out. So you don't have to supply the continuous variables out. With that, I don't know if this didn't work or that was just because the torch was not defined in some fashion. So this I've said 128 batch size, 128 batch size here. So it's going to load 120 rows of that data every time with an array of categorical variables and a continuous variable, and then the y. And the len of this, don't worry. So there is 879 batches because we have 150,000 rows, and then we are taking 128 batches. Each mini batch is 128 rows, so there'll be 879 batches that'll go through. See, okay. Here's where some categorical levels are a lot more levels, and the store in particular has over 1,000 categories. So he's going to come to that. So what is my cat size? So he's going to say, what is my cat size for each of the categories here? That's what he does. Say store cardinality. How many categories are there? For stores, there are 1,116 stores in that different stores in that data.
So you add one?
Day of week is
So you add one. Why is it 8 instead of 7?
Or 9. And
then I'll this one.
yeah,
So one extra. Okay.
one extra. Len
He had a
Johnson,
maximum,
the-
right, of, how long, so he's not gonna use all 1,000. For the embedding length, it was like.
No, he's not gonna, that's what, minimum,
50,
the 50.
right,
Or C+1/2 he's
Right.
using.
maximum of 50 or.
Not maximum of 50. He's actually using more. Because it says minimal. We use the Carnot which will, there is a number of unique value to decide how large to make it somebody. Each level will be associated with a vector with length as defined as bow. No, he's only have 50. So minimum.
Yeah.
Oh, it's
So,
not.
Yeah, if it's larger than 50, then it's at 50.
Oh, yeah, minimum. Yeah, not max. Yeah, 50. So for 1,000 thing, he says it's 50. If it is 8, then he uses 4.
Yeah.
Because it's that or the half of that. So that's what he got. So that way he's now able to reduce the size of that one hot vector. You would have had to use 1,000 one hot, 1,000 size, zeros and ones, and that's very inefficient. Memory occupies. You can do that. Okay. Embedding size minimum. So he's got the embedded size with the
Right, size and coding.
yeah. Now, this is the what he does is he has to initialize that embedding layer. So that's the weight, the data weight, the x.weight.data is the value of the weights in that layer.
So,
And he's saying this is the initialization of that.
so what is that? Is that random or?
He's doing a uniform. I mean, he's saying 2 divided by x dot size of 1 plus 1. So this x equal to x dot weight dot data size. So he's saying 2 divided by what is the size would be, whatever is a 50 or 2 or something like that. He's saying 2 divided by, so that will be 2 divided by 51 or something like that. That's what the SC would be. And he's saying it's going to be, I think that's what this is, but we can check that. Because this is where, this is the start of the deep learning layers here. And he is going to do the embed init of the embedding layer. If you see, this is the nn.embedding. So we should look at what nn.embedding looks like.
Right.
He creates,
Yeah, how does he get the numbers for that? The embedding is like the kernel in the CNN, and it updates like the weights, right?
yeah, it's like it's updating the weights. That's why you are learning the embeddings.
Right.
So let's look at what embedding does. I mean, that's the key thing for him is, source. Module is often used to store word embeddings and retrieve them using indices. The input to the module is a list of indices and the output is the corresponding word embeddings. So what it does is it's going to throw out, let's just look at the source. Containing 10 sensors of size 3, a batch of 2 samples of 4 into the variable torch long tensor. So he's saying 1245 4329. Embedding of input. This is what happens to it. First, when you just say embedding of that with whatever it has, with the weights it has, the learnable weights of the module it has, it will represent it as, what are we seeing here? 1 Yeah, 3. We are asking it to represent each value will be represented by three embeddings. So I think this is what is happening is 1, 10. What is a 10? NN dot embedding of 10 containing 10 tensors of size 3. Batch of 2 samples of 4 indices, a batch of 2 samples of 4 indices each, because it's giving you 2 times, yeah, those are the 2 times 4 times 3. I have to assume as this is what is the, these are the, this is the embedding for 1, this is the embedding for 2, and this is the embedding for 4, and this is the embedding. That's the result. That's what is codifying 1 as a set of, because each, what it does is when you give 50 or whatever 10 embeddings, it's going to codify each category number, whatever number it is, as a set of a vector of 10 that varies from -1 to 1. Or this one goes from more than 1. So it is not -1 to 1. I thought this was -1 to 1. But
is that a random initialization?
yeah, that's a random initialization. See here, this is what it's getting initialized. What is it getting initialized by? Self.weight, parameter of torch.tensor num of embedding dim, number of embeddings, and then the embedding dim. So what is the number of embeddings? Let's just make sure we understand that this number of indices to extract per mini batch, embedding dim, n is okay. There's the mini batch, and then the number of indices to extract per mini batch, and then they say output is n w embedding dim. Number of embeddings, size of the dictionary of embeddings. Okay. So that size would be the 1000. And then the size of each embedding vector is your 50. That's what it's doing there. And then if you want to give padding and all that stuff, and if a given pads the output with zeros whenever it encounters, what is it? So ultimately, if you go here, you have to look at what it actually does in initialization. What did it say here? Padding. Whenever it encounters the index. Pads, if given pads the output with zeros whenever it encounters the index. Oh, okay. Okay. So you could say, hey, don't do anything with that index, make it 0 or something like that or something. I think that's what the padding does. Max norm, if given renormalize the embeddings, always have a norm less. Yeah, there is a lot of things they go, the p norm and scale grad by frequency. This is scale gradients with the frequency of the words in the mini batch. I mean, you have to get deeper into this things too. I mean, the main thing is these are the 2 things. If you look at it, you have to give the number of embeddings and then the embedding dim. Those are the only 2. Everything else is by default. They have default values for that. Is what is my, that's why he created here. If you look at this, because he needs to give that, that's why he has created this embedding size vector, which is the first is the number of embedding. And it's the number of what do you call number of embeddings was 1116, and then the embedding dimension is going to be 50. That's why he uses this, because he needs to give that for that layer. And what it does, if you look at this, reset parameters, self.weight.normal 0 to 1. That's what it's doing. It's making the weights go from 0 to 1. And it's doing it a normal. It's just saying, hey, give the weights and make it a normal, normalized between 0 to 1.
So those weights, the numbers, they represent location and
Hmm?
dimension.
What?
So the weights, the number, the entity embedding numbers,
Yeah.
they represent a location in n-dimensional space or?
Yeah, this weight, see here the parameters, it's a number of embeddings and the embedding dim.
Right.
So the weights are going to go from, let's see what the weights are going to go from. Because if they are creating the weights parameter of number of embeddings and then the embedding dim, it's doing this. It's doing, hey, it could be 1, 50, 52 and all that stuff. That's my, so it's mapping that to a 50. Say this is, well, let's say a 10 embedding size. So it's mapping it into a 10 embedding thing here. And then the 50 here is getting its own. So this would be, I would say this would be this many weights going here of 1. But I just need to know, I want to see, is the weight, how big is the weight? Because when I look at this parameter, it says number of embeddings and the looks like the vector is, hey, I gotta have, if this went, or we could, let's make it a little bit. Let's start with a simple use case. Let's just start with 4 and we'll do two embeddings. Let's start with 4 categories, which could be 1, 2, 3, 4, which is fine. And then if this is 2 categories, 2 embedding, it's going to be represented by 2. This is going to be represented by 2. And this is going to be represented by 2. So are we having
2 bits, basically.
2 bits here? So that means your weights are, I'm going to have the weight matrix weight would have to be 4, 2. The weight, what is the size of the weight matrix? I'm trying to say, hey, this, because it's saying the parameter is number of embeddings in the embedding dim. So that means I'm going to have this many weights going from here, here. I'm going to have this many, I'm going to have 8 weights basically. Because I'm going to have W 1, 1, W 1, 2, and then W 2, 1, W 2, 2s, like that. For each thing, it's going to connect me like this, the weights. So it is different from what we have. So how does it in a neural network, how is it connecting? Like, because usually we have the inputs, then we have a layer, and then each one will connect to this. So it's similar to that. I mean, I'm going to have, say I have 4 inputs or something. Well, that's not the embedding layer. It's almost like saying that I have a 4 input and I only have two embeddings. I'm going to have this. 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 Yeah, it's slightly different. I mean, here when we look at the neural network, we would say each one is an input. Here it's saying each one is a category, and it's identifying the weights for this, for each category. It's identifying weights for each category. So it's unique. I mean, it has to apply. It has to find a weight that's unique for each one of them. I mean, as it trains. I mean, it starts off with some random value because you're just initializing this random value with normal 0 to 1. So you're gonna.
So each square is an entity embedding value, or this
Yeah, this is yeah. So what will happen is one will be represented by, say, minus 0.5 and say 0.1. And then this could be represented as 0.2 versus minus 0.3, something.
Yeah.
But when you start off, it'll be something random numbers. But when you train this thing, if 2 was somehow closer to 1 in the category in which if it finds, then the weights will get trained so that these numbers are closer together. And if you do a cosine similarity between those two numbers, it'll be closer to together.
So the weights get updated, which in turn update the category and then.
Yeah, it is going to, yeah, this category, these things get updated because the weights are getting updated. Because this ultimately, what happens is this is the number, ultimately, this is what is flowing through the network now. Because we'll get the numerical variables, all the numerical variables coming here, and then we will we'll concatenate it, and then now go through a normal neural network layer.
Yeah. Now this is good, because I thought the embeddings got updated directly, but it's the weights first, then which update the embedding.
Yeah, the weights get updated, and then the weights based on the calculation, then this numbers change. So it's calculating due to the gradient, applying the gradient thing.
Yeah.
Gradient algorithm, it's getting updated. So it's just a way of representing. So I don't have to have. So the way is with the embeddings, I don't have to have. I can represent this 4 or even 50 with two numbers,
yeah,
rather than have a 50 one-hot encoding thing.
It could be 2 or it could be 3 or 4.
Oh, it could be 3. I mean, you can choose 3 embeddings and stuff like that. Like when we did this, we had 1,000 categories and we only chose 50
Right.
numbers to represent that. And he says that's pretty good. I mean, a 50 embedding is going to get you quite a bit of range. Because you are now playing not with 1 or 0. You know, one-hot encoding, all you could play with was 1 or 0. Here you are playing through the whole, because I thought it would be bounded between -1 and 1, I think. So, but it's a continuous range of -1 to 1. So you can put in a lot of different codings into that.
Yeah, more in-depth representation.
In-depth representation.
So those numbers in the entity embeddings, they can be mapped in the multi-dimensional space, right? And that's where, if they're close together, you know there's a,
Yeah. It's close because you can do, once you find, say, if this was 3 or something like that,
yeah,
you can map that, or you can do, I mean, if it was 2, you can easily map it, but if it was 3 or 4, you can do a PCA, principal component analysis on it to get it to a 2-dimensional space.
Yeah.
And then when you map it, you will see things which are closer. This category is close to this,
so like Saturday and Sunday
will be close together, and yeah. And the NLP is a pretty big thing in the NLP, because that's how it finds out how the words are close together, because it's seeing these words, hey, this word occurs after this word when you're doing the RNN and stuff. And then when they use it in the recommendation system too, he uses that in the, I mean, everywhere else other than the image thing, you'll get into the embeddings all the time, because it's a compressed way of representing a very rich set of categories. I mean, a very high dimensional category can be represented by a very small amount of embedding. So all they're doing is, because what he's doing is reset parameters saying, hey, let me just say self.weight.data.normal 0 to 1. So it's assigning a normal thing. And then usually the underscore means when Jeremy says that, hey, that's in place, it does it in place. You don't have to do self.weight.data equal to you just put a underscore and it'll do it in thing.
So when it's from 0 to 1, is it always 1 decimal place? For the embedding entity?
No.
Is it more?
Oh, it has a lot of decimal places. I don't know how much decimal places. No, it is a rich.
Is it more decimal places you have?
It's a floating point.
Oh.
It's a floating point. That's why float 32 or something like that. So yeah. So whatever, if it's a float 32 or whatever it is, it's going to represent that. See, number of embedding, size of each embedding vector.
It's like the more
Yeah.
decimal place, the richer the.
See here, they show like 4 decimal places, but it can go more decimal places. They're just showing 4 decimal places. It's all the float, whatever the float value, if it's a float 32 or a float 64 or whatever it is, that's what it's going to represent it as. And so this is, yeah, and what he does is, and then the padding, I mean, this is what it's doing. Hey, I'm self.weight and max norm and norm type, grad frequency and self backend embedding dot apply. And he says, well, I don't like this. He's going to change. He changes this. He wants to be a uniform size. He's doing that embedding initialization. He's taking the weight dot data. Instead of normalizing it, he says, I'm going to take this size of the one, I would think it is in the first dimension or something like that. And then he's saying 2 divided by that. And then I'm going to do a uniform thing on that. So the weight doesn't seem to be, so if it was 2, it'll be 2 divided by 50, and he's going to say minus 2 divided by 50 to plus 2 divided by 50 would be his range. And if it's 2 divided by 10, 12, yeah, it's something, yeah, 2 divided by, he's just doing that. I don't know the reason. I mean, he feels instead of normalized thing, he feels this is better. Then this is where the real model starts, where he's saying, hey, I'm going to have a module list is I'm going to have an embedding layer for in the embedding sizes. I'm going to have as many, because remember, he's defined all the embedding sizes here. And so that's my, and then that came from how many category variables were there. So he's saying, I'm going to have that many, as many of that, of that embedding layer, as many embedding sizes are there. So he creates that embedding layer there. And then he's initializing the embedding. And then he's saying some of E embedding dim. N, he's just a number. Okay, how much dim for size in this self dot n dot equal to, okay, he's just keeping track of how many embedding layers are there, I suppose, and then how many continuous variables are there. So he knows the number of embedded layers means the number of categorical variables. And then he's combining both the sizes of the number of this plus SCS. I don't know what an SCS, where did he define the first SCS? Yeah, it's in the initialization. It's when you define the thing, I suppose. And then the linear, then he's just doing a linear model here. And then he's creating a linear model, sizes of I, size of I plus 1 for I in range of size I. Okay. He's combining it through a linear layer. He's just, and then he's doing a batch norm, and he's doing a, he's defining some normal, K-mean normal thing on the linear self.linear. He's also defining a he's initializing the weights of this linear layer. And then the output is a linear layer. Again, he's also initializing that output thing. And then he's dropout. He's doing a dropout. He's doing a module list, drop. And then he's doing another batch norm. And he's doing, I mean, if you look at his thing, if you look at this code, I mean, those are all the definitions. This is how the forward thing goes. In all the embeddings, he's saying category E of embedding of all my category variables that comes in through the input, category variables. And then he's concatenating all the outputs from all the embeddings together. And then he's making it go through a embedding drop layer, which is just a dropout layer. And then he's coming back to the continuous variables, and then he's doing a batch norm on the continuous variables. And then once he gets the output from the batch norm of the continuous variables, he's again concatenating the embedded, the categorical variables that he got from here with the X2, the continuous variables. And then he is applying, what is he doing? He is doing zip, linear drops, batch norm. He's doing for LDB, he's doing f dot relu, L of X. L is the linear layer, so he's doing a relu on the linear layer. And then he is doing if self dot use, if we said use bn here in the initial thing, then he's putting it through a batch norm here. And then he's doing a dropout on that. And what else? I mean, once he gets it out, it's not as self as regular, is multi sigmoid. I think he does is reg is true. If not self reg, if it is false, then he does that. But if not self is reg, he does this. If that regularization, there's some regularization or something, I don't know what he's doing here, but this is the one we usually follow because he's putting the reg as true. That means it's going to come here. He's doing a sigmoid on the X, the output. And then he's saying Y range. Self.Y range minus he's also, okay. Okay, so the Y range is where I forgot Y range. Okay, if that Y range was none, okay, then he's not even doing anything. Okay, this is something, if that Y range or if there is a regularization, but if all that Y range was none and stuff, it'll just return the X here. It's just going to return the stuff, because when we look at this, Y range is equal to Y range. Okay, so he's saying what is the Y range? He's defining this as the max of that YL, and the YL itself was EXP of something, I thought, of the Y. He's defined the YL here. Where did we define it? We defined YL here, which was the log of Y. So, because ultimately he's saying is, I need a Y. I've made it into a log of, I made it into a log of Y. And then he's saying the max of YL. And then he's saying the Y range is 0 to max of,
The highest cell.
yeah, the highest cell value, he's saying that goes from 0 to that. The Y itself goes from 0 to that. So he's going to scale the output. He's going to take a sigmoid of the X. The sigmoid goes from 0 to 1, the 0 to 1. And then he's going to scale it to that Y range, basically. Because he knows the Y is going to have this range. So he's scaling it so that he can calculate loss function. Okay, so that's what he's doing. He's just compressing that value. Hey, I got an output, putting it to a 0 to 1 thing, and then scaling it out. And then here's what he defines the MSE loss. It's just a mean squared loss. He's defining on that. The outputs in the target. I don't know. This is an RMSP. There was an exponential root mean squared error too. I don't think I used it in any way. I think I just used the f.MSE loss. Because that essentially calculates this thing. So metrics, that was for the accuracy metric. Okay. Exponential root mean squared loss. because the Kaggle competition says you have to calculate the accuracy based on this exponential mean squared loss. This definition comes from the Kaggle competition. This what the root mean squared error, this one comes
That's the
from,
metric they use.
that's the metric they use. So if you see, the y range is from 0 to 12 in that log of that y. So here's where we define, hey, I'm going to define the mixed input model because it's the mix of continuous and categorical variables. So there is an embedding size, and then my continuous variables, how many continuous variables are, the continuous variables are the length of the total DF columns minus the categorical variables will be my continuous variables. And then he's doing this dropout thing, 0.04. I think that's what the 0.04 and 1. Yeah, embedding drop, that's the dropout, how much he wants to drop out. And then the outsize was used for what here? Outsize is 1. Did he even use this outsize? Out of size. Yeah, outsize is just, I think, output of X, sigma. No, where is the outsize here? Oh, the linear model. Okay, linear model. So that it gives us only one output, basically. That's all he's defining. That he's just defining it as outsized there, and then the 1000 to 500 would be the sizes. And what's he using the sizes? SCS for, yeah, embedding plus counted plus 1000. So that 1000 is what he's defining his linear layer. That how many hidden thing he's saying, hey, I'm going to define the hidden layer as sizes. Well, sizes he's actually defining as 1000, 500. So that one, the sizes he's defining this plus this sizes. So what happens to, then he's saying 1000, 500, and then NN linear of size of I plus size of I plus 1. Okay. For I in range of ln of size of -1. Okay. So the size of I thought would be modulus NN layer in range of len of sizes -1. Len of sizes is 2. Okay. Size of I. Okay. So he's defining 2 linear layers as it goes through. So the way he's doing it is, he's saying, I want a linear layer that would give SCS of I and SCS of I plus 1. So the input is SCS of I, and the output is SCS of I plus 1. So he's creating this NN embed plus NN cont in there. I mean, we can easily see what is happening. Let's just do that in a cell here. N embedding is equal to Yeah, n embedding was, I mean, we know this, n embedding is probably 1, 2, 3, 4, 5, 6, 7. I mean, I'm just going to say 10 if it was 10. How do I do this? N embedding equal to 10. I can do the n count. Okay, just for thing, I'm going to say 20 on that. And then I'm going to say SCS is equal to 1000. Okay, SCS is equal to 1000, 500. If I do this, the next one, if I do this, if I say SCS is equal to actually this plus this, so all it has done is it's created 30,500 basically. It's just added up, hey, the 10 and the 20, those are my input things, the continuous and the categorical variables, and then it said 1,500 now. So what it's doing is it's creating here in a linear layer. So it's going from 30 to 1,000. And then the next one, it's going from 1,000 to 500. So it's creating 2 layers, basically. It's creating this.
The whole model is 2 layers.
Huh? No, not the whole model is not 2 layers. When you see the whole model, the embedding is coming here. See, there is an embedding, I mean, you get all these embeddings and then concatenated. These embeddings are concatenated, yeah. Okay, they're concatenated. So many embeddings. Let's say these are the cat wares, and then the can't wares. So you get these things. They're concatenating, and then he's saying is what they're doing is then they're sending it through a 1,000 layer linear layer, linear. So it all goes into a fully connected 1,000 layer, linear. And then after that, he's then creating a 500, this 1,000 linear, 500 linear. So all that is coming here to 500. So he's creating, first he got the embeddings done for the cat variables. And then what he did is, if you look at this, as we go down, so then he has concatenated. All he has done is he's done a, I mean, in this categorical, before it comes here, he has done a dropout layer here. You do a dropout layer, and then combine it with this continuous variable, and then go through 2 linear layers, basically 2 linear layers. He goes through 2 linear layers, and then he does a ReLU on. He's defining 2 linear layers, one going from 500 to the before, but what he is doing is, it's not a linear layer, but this 500, it's actually what it does is it goes through here, 1 linear layer, it goes through, so you have a basically linear, say if this was this was 30 or something, 32,000 linear layer, and then that comes out through, if you look at that, the next he applies a ReLU on that. ReLU on that, then he does a batch norm on that, batch norm layer on that, and then there is a dropout layer. Then you go to another linear layer of 1,000 to 500. And you do the same thing over again. ReLU, B norm, dropout on that. So this is one set of stuff with this 1,000 layer linear layer he does. And then after this dropout, he goes to another linear layer from 1,000 to 500. He does all that. And then at the end, he says, okay, now I need to come down as, what is in the output layer, which is defined. If you look at that output layer is just going from 500 to 1, basically.
So the values.
Our output layer is just going to, then the output, you do these same things here, and then you come out, and then he says, goes to linear layer, which is 500, and then 1.
So the 1,000 and the 500, the values, where does he?
What values?
The 1,000.
He's just saying, hey, I'm going to start with 1,000. Yeah,
So he just sets that.
he just sets that, hey, this is like, these things work. So I'm going to do 1,000 layer linear layer. And then I'm going to bring it down to a 500 level linear layer. And then, but in between, I'm going to do a ReLU, I'm going to do a batch norm, I'm going to drop out. So this is all non-linear ultimately. And then he's doing another linear with the non-linear stuff. And then he says, okay, now I got to get to 500 to 1, basically. That's the whole structure, basically. That's all he does in the time series thing. Once you prepare the data, he's saying the cat variables and the continuous variables, I do a dropout on that and then combine with the continuous variables. And then I send it through a linear layer.
Why do the dropout on in the very beginning?
Very beginning, I think he feels maybe there's some kind of a regularization. I mean, dropouts are always regularization. So some of these things, it's like there is an art to this. So he doesn't explain why he exactly does a dropout layer.
And to help with
Because I can see there is a dropout here. See, it goes through an embedding not equal to 0. It goes through a dropout after getting the categorical variables. And then the continuous variables, he does a batch norm. So for the continuous variables, he's doing a batch norm. Right after, he's doing, like the same way we said, there is a dropout here. He's doing a batch norm here on this. And then combining these together.
Well, batch norm makes sense on the continuous.
Yeah. Yeah, you can do batch norm on the continuous. But this dropout, he's only doing it on after the embedded embeddings are done, he does a dropout. I have no, but yeah, I mean.
To prevent overfitting.
Overfitting, maybe.
That's
Maybe
why it's
you
done.
just try a few things, I suppose.
Is there another reason to do a dropout other than
Should
to
be
prevent
able-
overfitting?
Should be
Usually.
overfitting, I think.
Yeah, to
That's-
prevent
that's-
overfitting
that's
is
the
usual.
reason.
The usual reason is to prevent overfitting.
You want me to put that line?
And then the dropout is a very small dropout. If you see here, it's 0.04. So he's not doing a big dropout like 0.2 and stuff. He's doing only a 0.04 dropout on that.
0.04?
Yeah.
Okay.
0.04.
Usually in CNNs, they do
Huh?
much higher.
Oh yeah, much higher in the CNN. So he's doing a very small dropout here.
Right.
Huh? 0.04.
That's very low. That's 4%. only.
4% gets reset to 0.
No.
The connections are.
The connections are not there.
Yeah.
That's all there is. The connections are not there. All he does is if you look at this, the dropout, so you won't get 4% of the values of that categories won't come out, basically. It'll drop that thing out. It's not going to come out. See, this is the drop. Drop out of the embedding drop here. And the embedding drop was that
I mean,
0.04.
isn't that equivalent to resetting it to 0 by the time it gets to the other layer?
Yeah, it is just dropping 4%. So when it comes out, these things, Yeah, it is resetting to zero or something, yeah. The weight. Yeah, the weights, the thing is, the weights don't get reset to zero. It's just that when you do the dropout, it's randomly selecting something and saying, I'm not going to calculate the thing on that, I suppose. It's just dropping that. It's going to come out as zero. It's going to come out as zero. Huh? What?
I'll have to read up.
Yeah, you have to read up a
There's
little
some
bit.
laws and drop.
Dropout, and then the dropout was even patented by Google to prevent other people from this thing. So yeah, well, they said they are not going to impose that, but it was an invention of Google DeepMind and stuff, this dropout concept. But it's such a powerful regularization that they didn't want somebody else to go and patent it and not. They're still not going to enforce that patent, but they are preventing other people from, yeah.
It's not always about collecting from your
Patents, yeah.
It's a lot of the times it's from preventing other people from blocking everybody else.
Yeah, everybody else. So that's the thing they're doing. So that's all he does. I mean, if you look at all the stuff, and then it goes through, basically, I didn't say that, okay, the output comes out, and then he does a sigmoid on that. I suppose he's just saying, hey, I don't like the output being 10 or something. I mean, I do a sigmoid on that. There's a sigmoid, and then he scales it out, basically. There's a sigmoid here. Sigmoid. He does the sigmoid. Yeah, after this one, then you do a sigmoid on that. So you'll get some crazy number out of that. It could be 100 and stuff. He scales it to 0 to 1 through the sigmoid. Through the sigmoid, he scales it, but then he again rescales it 0 to 1. And then he rescales it using this Y range, the range of that Y. Whatever was there, he rescales that 0 to 1.
And that's their actual prediction.
Actual prediction
Sale.
of the sale. And then he does the loss thing. So that's all, yeah. There is only one number which comes out at the end of the day from doing all the stuff. One number comes out, which is the sales. And then it's going through and adjusting all the weights based on that one number. But obviously it gets a very good accuracy and all that stuff doing that. But this requires so much feature engineering and stuff before you can even get here. Because it's...
So can, from a generated model, is there an easy way to determine which categories actually matter?
Which categories actually matter?
Yeah.
I mean, you can do, I mean, I don't know how they would do. It's not like a random forest, they would say, where you can actually go and see which one has higher importance and things. In this deep learning, I haven't seen where they have actually said, okay, these categories are matter more than the other categories, except unless you do something.
And just type in.
Yeah.
Change one category.
And see if it affects anything at all. Yeah, you can do that, or they have that line. See, that line thing will tell you how it came to that answer. Say you put something here through this, the LIME will recreate a decision tree. This is the LIME library. So that's a very useful library called LIME. So if you look at this LIME library, LIME, explaining complex machine learning models with LIME. LIME with PyTorch will come. Explaining the predictions. So what it does is it goes through and says, what kind of tree could I trace to get the same answer? But the tree will change every time you give. It's not one tree. The deep learning model is learning so much complex things. It's not one tree. But it'll tell you what kind of tree will get you that answer. So you know in that answer what was most important.
Well, the reason why I want to know this part is that all of these features get engineered, but then you
Oh,
might
yeah,
not
you
need it.
need all that stuff,
And say
yes.
you want to run this model in real time,
Yeah.
you would have to enrich.
Oh,
your
enrich
data,
all the data, yeah.
And
Oh, yeah.
it will be slower to go out
Oh,
and
yeah.
hit some
No,
Google's APIs.
you're right, you're right.
Now, a lot of it you could preload since it's a date, right?
Yeah.
But
I mean,
that's not
the way you could maybe see it is, I don't know if you can see it inside. I'm trying to see if you can maybe see, come here and see what are the weights of these, but then you're looking at 1,000. I mean, I'm trying to see how do you see.
I guess the ones
you-
that don't have any weights going to any one of the 1,000 will
how do you do this?
sum up the weights
Yeah, sum up the weights or something
from
like
each
that.
category.
From each category, I mean, each thing, each one it has a weight attaching itself to 1,000 things.
So it becomes more difficult. It's an embedding.
It's
so
an embedding.
It becomes more difficult.
It's an embedding, that's fine, but then the embedding, you know, this is the embedding for this category. This is the embedding for this category.
Yeah, but it's in 50 different.
Yeah, but you've just
Variables.
attached it, yeah, 50 different variables, yeah.
So it's not
Yeah.
necessarily, I mean, it might assign, yeah, since it's, how many categories do we have?
We have maybe 20 or 30 categories, but then we are going through an embedding that is 50, could be different and stuff. So you would probably you would just look at what are the weights for this embedding, because if there are 30 category variables, there'll be 30 embedding layers that's going to come out. There's going to be 30 coming out with different dimensions. One could be a 50 embedded with 50 embeddings, and the other could be 4 embeddings, and the other could be 3 embeddings and all that stuff. So the thing is, okay, let me look at this, the weights associated with these, the first 50 which belong to my first category or something like that, and then the next 20 or the next 2 or something which belongs to the next category and all that, and see is the weights. But the weights are also, yeah.
If you didn't have embedding, it would be easy to see. You just see which one has no weight to it.
Yeah. Yeah. But the
Which
embeddings are the
feature,
key
right?
things here. Yeah. Embeddings are the key things. But all I'm saying, all I thought was, could you not see these embeddings? Because these embeddings are, ultimately we are concatenating all these things, but there is a set of.
No, you could go through and
Go through and
actually use an embedding.
Use an
And
embedding.
then sum up all of the weights.
For this embedding.
Or multiply.
Multiply.
Yes.
Yeah,
by the-
multiply
by the-
that. With that, I mean, send one thing, send one input data, and then multiply, I mean, see, okay, what is this? How much value is this and how much value is this and stuff. And see which one has a higher value, and hopefully that higher value will carry through and stuff. So,
And then you can drop the lowest ones.
Some method
Yeah.
that they use.
yeah.
Feature selection algorithms, yes.
Okay. In the deep learning model?
Yeah,
Yeah,
for
this is-
different ways
yeah.
to pick important variables. Online, I Google.
Okay, no, that'll be good. What's
But
the
it's
link?
not-
I mean, we can
If you go down,
look at the link.
if you go down, when they talk about the
Feature selection
yeah,
for deep learning.
try I didn't put deep learning, but you should.
Yeah, because deep learning, because feature selection for other things are easy.
It's easier.
Easier.
Much easier.
It's deep learning is the one which is using.
It would be nice if there was a library.
Okay, deep
features
feature selection. The
once,
insert layer of connected to
matter
each feature
most-
before the first hidden
for
layer.
your output.
What is happening?
You only have one.
Yeah, I mean,
Okay, basically what you said is, he's saying is, okay, one input, add some noise to it and check the accuracy again. Repeat this for each input and see how the noise versus the predictions. So you change each variable by a little bit and see how the result is changing.
We need this in the libraries.
Yeah. Because if an input is important, then the extra uncertainty due to the noise will be detrimental and stuff. And so your prediction should change more as you input.
Well, he only got 6 likes. Maybe he has a better.
Yeah, there's a better one. Yeah, I know.
I see one with like 100.
Yeah.
Maybe not in this. But you got 0.
Maybe check the papers. They use dropout to rank features. Our method creates a similar effect to feature bagging and manages to rank correlated features better than other non-bagging techniques. So we compare our methods to random forest to derive importance in deep learning, such as deep feature selection and various heuristics. Okay.
So it just runs
dropout to
random
rank.
forest on it, and
But that's what like a Lime does. Is what it does is a random forest. That's how it tells you, not a random forest. It does a normal decision tree model into the thing and says these are the important variables. This is how it traveled through to get your answer. So that's one way to kind of know, hey, you put this result, and see which one. Anything, okay. Oh, he put something else. Applying highly accurate facial recognition. I think I've seen this before. This is an old article. So feature selection using deep learning, is that what we saw now? Or?
Yeah, that's
Okay, in machine learning, a new perspective. I want deep learning because machine learning to do away with what does this guy have?
Deep learning methods of features.
Okay. Was there another article?
Yeah, right under there, the core.
Here?
I don't know, the link above.
This one, what are the deep learning methods of feature selection? Autoencoders and keep the last hidden layers as your features. Unstacked RBM, deep belief network and keep the last layer as features. Okay. We have to use stacked autoencoders and keep the last hidden layer as your features. Yeah. Okay.
Maybe you can come up with a library.
Yeah, we'll talk about that. And search for it. I'll search for things and see if there is any better way of. I have to imagine this is the only. You just keep a noise and stuff and see what changes. But then that is the same as the Lime approach, because you should try the Lime. We should try the Lime and say, I haven't tried the Lime. I should try that.
What
and
is
see.
That technique or library, whatever, that changes the parameters to see which parameters to use?
That's grid search.
Grid search.
Yeah, but grid search is not, but it only changes parameters. I don't know if it'll change all the inputs.
Because you create something similar to that to
yeah. You can write something, I would think. You take all the variables and you write a function with saying, okay, change this now, and what is my value, change the next one, put it in a loop, and then get all your predictions and see how much delta did it change by, and say, hey, this delta I changed. Change every. Hopefully, all your features are because we have put a map around to it. It's all in the same scale.
It should be pretty quick. Because
yeah.
You're not training it.
You're not training it. Yeah, you just say, hey, I want to increase this by. If it's all into within, say, 0 to 1, or if it's all normalized in the 0 to 1 or some other way, then you say, hey, I want to increase each one by 0.1 sequentially going through. The problem with all this stuff is that's just looking at one variable at a time. Usually there are in deep learning and stuff, because the nonlinear nature, you'll have multiple variables having effects that you won't be able to find just by changing one after the other. So, I mean, you just have to.
Well,
that's the problem with the deep learning. It's very difficult to
it's,
know what is deep learning has that problem.
That's why they're adding noise to your regular data
set. Yeah.
Instead of keeping everything the same.
Yeah.
And varying one at a time.
Yeah.
You just add noise.
Yeah.
To each one separately.
Yeah. Yeah. Yeah.
So you'll still be able to find, or at least get an idea of where they are.
The connection between variables.
If there is something that only gets affected by noise when the other feature is in a certain range, you'll find it at least a little bit. You'll be able to see it.
That's the one I was looking at, but it's not.
Okay, but this is all for normal stuff.
Yeah.
Statistics. I mean, those things are pretty. I mean, there are. I mean, you go to, even if you go to random forest and stuff, you can actually, there is a sklearn has a thing, tell me all the feature importance, and it'll tell you which features are more important than the others and stuff. So yeah, see, importance features. So this is not applicable to, he does a random forest, exactly as I said, random forest, and then you predict and you just say importance and it tells you which one is important.
Or maybe.
I mean, this is, something like that would be very cool if you have something like this, define a life.
Just write maybe you should just run a random forest on it and find the.
Yeah, that is also another way. I mean, instead of running the deep learning, because the deep learning gives you a better, accurate model, but just run a random forest on it. And before you run, see.
It didn't matter at all. Probably still doesn't matter.
Matter in the deep learning. I mean, it matter more. Well, maybe not. I mean, so maybe just fit a random forest onto this and see what the importance, and then that you can say call the thing, so that at least you have some idea. Okay, these are let me take the first 20 variables that are important, and then run my deep learning model and see if there is any big difference in the accuracy and stuff. So.
I have a question if you have a few minutes, but it's separate from this.
Oh, from this, okay.
So we can finish.
Okay, this is all, there is nothing definite. I mean, the same thing. Once you define this, you just go through the optimizer and you go through the Adam, and then you put a trainer on top of that with, and then we have already defined the loss function and stuff. And then, I was just trying various things. You just you do the LR find again on this, and you do the LR find, you get the thing, and you say 0.01. Hey, I want to train it on 0.01, and you get the accuracy. It keeps improving every time you run it.
Is this the Adam, the improved Adam?
No, this is just the old Adam. But you'll see, you start off with 0.74, and it goes to 0.85, 87, 88. I mean, it's just you'll get pretty high accuracy, 89, and I think he gets to 90 or something. I didn't go. Then if you do a few things like all the stuff that we have discussed before, the cosine thing, like changing the learning rate in a cosine methodology and stuff like that. So, and then what he does is, this is what he gets this trained on a subset of that data, so that it's easier for him to train initially. It's faster to train. Then he says, okay, that's the same model. Now I'm going to increase the data size to that 850,000. And then he trains that. That's his technique, saying now I can train it faster because I've already trained it on a subset of data that is supposedly from the same sample, from the same population. He's not starting from scratch. So I don't need to, then he's saying my thing will train faster. I don't need to run that many epochs and stuff.
It's almost like transfer learning.
It's almost like transfer learning. Yeah, it's almost like transfer learning, but it's not transfer learning in the sense he's doing it. Transfer learning was, hey, I've trained it on some other data set and I'm using it in my data set. This is just saying I'm going to train it on a smaller data set so that I know, because he's saying I can go quickly seeing what works and what not doesn't work quickly.
You don't have as much data.
As much data, so I can change things in the model and stuff and get some result. Then once I am satisfied, then I'll put the whole data and then run it. And that's a useful technique. I mean, that's how he says, hey, just use a subset of the data, but do all the things. So don't start with the whole thing that it takes 3 hours to run even on a GPU, and then you don't have enough time to experiment. Yeah. So it's pretty, I mean, he has very practical examples. I mean, he's very practical in his ways. He says, how do I do this? How do I do that and stuff? So then the next one, I mean, we can talk about the language model next week and stuff. He has the language model, which is pretty complex. Okay, I don't know whether we can go through it, but to understand it becomes very complex. It's better actually to go and use this character RNN, that you can actually understand what's going on. Because a language model, in fact, it covers a lot more in deep learning too. But so what I thought was I started with language model. Then he uses all his libraries, and it was getting hairy to understand what he's doing in that library and stuff. But then I understood. Then I went to the RNN model where he used the character RNNs. That's how he says, how do I develop an RNN from scratch stuff. Yeah, that makes it easy to understand how an RNN works and stuff. And a character is easy to understand rather than a word and stuff. So he takes a text and breaks it up into the characters. And then he says, hey, I want to know. I'm going to take the first 4 characters. I'm going to predict the 5th character. Or I'm going to take the first 7 characters and predict the 8th character. So, and that at least makes the understanding of RNN very easy. So it's better to jump into that. And then they also will talk about the recommendation. That's a pretty easy stuff, that recommendation model. Recommendation model is pretty easy stuff.
So, quick question.
Yeah.
This is a very, it's a simple question, but
yeah.
So the folder structure for the data, right? So you have your training folder, your test validation folder, and your test folder. For instance, with Cat, but he never uses the test folder, right? Because that goes to Kaggle.
Yeah, he never uses a test folder.
We don't even need it.
We don't need a test folder at all.
Okay,
we don't need a test folder. That
labeled.
test,
So if I wanted to use a test, well, I would need to label everything, right?
No. You don't label it. You can't use it. No, you can't use it. What you do is you have a test folder and then you send the test data into the trained model. That's all you can do.
But how do we know if it's correct or not, if it's not labeled? How do we know if the model is right or not if it's not labeled?
You don't know.
Yeah.
You don't know that. That's why Kaggle knows that.
But if you're not using Kaggle, if it's just for us.
For us, then you won't know it. All you have to see is you have to see it visually and say, did it predict the cat was a cat in the test data? Did it predict the cat right?
Okay.
Because the test is always, you don't know what it is.
Okay.
Or somebody, you know what it is. But even the test data, you know what it is, but you never used it in your training set.
Yeah, but we can label it, right? It's okay to label it.
Yeah, it is okay to label it.
Okay.
It's okay to label it because Kaggle also labels it. They know what the label is. That's how they are scoring you.
Yeah.
So
do you really need validation? So you do want test and validation, right? Because I know in your you only have test and training.
Validation and training. Because test is not really need. I mean, you only need 2 of them.
Yeah.
The other one is just so that for Kaggle, it's something you have to submit. That's your test data. Because what happens is when you start doing this, when you're actually in production, you would keep a test data separately. Even if you know it, you would keep it separately. You run everything on your training and validation because that's how you know whether it's overfitting or not. Because the validation, hey, is my accuracy on the training set higher than the validation means I'm overfitting. So then you do adjustments and all that stuff. Then you've trained all the thing. Then you go on to say, now I'm going to do something that the model has never seen and see what the accuracy is.
But to see the accuracy, we still need to label the test data.
We still need to label the test data.
Okay. I just want to clear because he doesn't do that. So that's just Kaggle.
He just, you don't need to That's just, hey, I need, you need to label the test data to know, but that's something the model has never seen. But the validation said the model has seen something. I mean, you've done something with that, and you adjusted the model based on, hey, is it, you stopped the model, the training in the middle and all that stuff.
So then if I wanted to use test data accuracy, I would need to rewrite the code to get accuracy from test data.
Yeah. Because really, because it all comes from Kaggle and you never write down. All you do is you predict and then you submit it to them and then they score you. Cool. Okay.
One quick question.
Yeah, go ahead.
That input layer,
Yeah,
the continuous variable part,
yeah.
that's coming from like the data, right?
Data,
That's the
yeah.
input.
Yeah.
But categorical variable, those are embedding matrix values, right?
No, it's also coming from the data. This categorical variables also, we are saying some columns are categorical variables.
Right.
So it's also coming from the data. Then what you've done is we have numericalized it. We have assigned, say, for store 1, store 2, store 3, or store 500 and stuff like that. We have assigned some numerical values to that because it could be store ABC and it could be store BCD and stuff. So we assign some numerical labels with key value pair. So this has something, and then we are putting it through an embedding layer. We are saying 1 doesn't mean anything to me. 1 is not like 1 in a continuous variable. 1 and 2, if store number 1 is 1, store number 2 is 2, they may be completely different entities. It's not like but 2 is just 1 plus 1. You can't do that with categorical variables.
1 is not greater than 2.
Yeah, so we can't. So then it goes through a embedding layer which converts that 1 and 2 and stuff to some code that you won't understand, but it's getting trained. Because through the data, it figures out, hey, 1 and 500 are close together. So it'll give very close, these numbers here for 1 will be close to the numbers for 500 because they are close, because it has figured out the sales, the way it occurs, the whether it occurs, or the how in the week where the sales peaks and all that stuff, they are very similar. So it figures out, hey, this embedding must be similar to this embedding. Because otherwise we can't, I mean, we used to, as I said, in the past, we used to use one-hot encoding for all these categorical variables. Now we are using an embedding, basically. And that only works, embedding only works if you can train, if it was not possible in normal machine learning before. Okay, how do you train? Because you've got to be able to train it. Because there's no way to figure out what an embedding is, other than by training through the data.
Before this, the random tree was the popular way to do this.
Yeah. So cool.
Yeah, it was good.
Yeah,
Thank
no problem. So hopefully David will be back next week.
you. Yeah, it should be.
Yeah. We lost 2 people today.
Oh, yeah, thanks today.
Yeah.
I survived on bar.